Welcome to CS320, the lecture for Chapter 7b. We're going to continue talking about Kleene's theorem. Now remember, Kleene's theorem states that if you could define a language in one of these ways, with a finite automata, a transition graph, or a regular expression, then you can define it in any of the other ones. Now we already proved that if we can define it in a finite automata, we can also define it in a transition graph, and that's just by the definition of a transition graph, because all finite automatas are transition graphs. Now, in our lecture for 7a, we already proved that every transition graph can be converted to a regular expression by eliminating the states until we end up with just a start state and a final state with a regular expression on the line between the two of them. So now we're going to do the hardest part of the proof, and that's step 3, showing that if we have a recursive or a regular expression, that we can create a finite automata that accepts the same language. So we're going to do this by proof by construction again, and in this way we're going to refer to the definition of a regular expression. So that definition can be found in your book in chapter 4. And if you notice, either the null word or a letter by itself is a regular expression. So we need to show that we can create finite automatas that accept the null word or just a letter. After we do that, when you create a regular expression, you have to apply one of these rules right here. Now the parentheses just for ordering the order in which you do the operations, but we need to be able to, since you can concatenate two regular expressions, we need to be able to take two finite automata, and any two, not a specific two finite automata, but any two finite automata, and come up with a way that we can concatenate them. And the same thing for unioning or oring, either a word in one or the other. And the same thing with starring a finite automata. So what we would have a finite automata that accepts some words, and then we'll modify it so that it accepts those words, but any number of factors of those words. So as you build up a regular expression, so let's say that we have this is a regular expression. So we'd start off with a finite automata for A. Well, B is a regular expression, so then we'll have a finite automata for B. And then we can union those together, so we'll use the algorithm that we're going to talk about to union those together. And then if we want to star it, we'll use the algorithm to take this finite automata and star it. So as you build up your regular expression, applying these rules, we'll be doing the same thing, applying the same rules, but to finite automatas. So to prove this, we need to prove that we could take any two finite automatas and union them together. That's what we're going to do today after I show you the finite automatas that can accept the null word and a finite automata that only accepts one letter. And then in the next lecture, we will see how we can concatenate two finite automatas together. And then in one more lecture, we're going to see how we can star a finite automata. So let's get started and create finite automatas that accept the null word and any letter on its own. So right here is a finite automata that accepts just the null word. Now I'm assuming the alphabet is just A and B, but if we have more letters or different letters in our alphabet, we just put all the letters in our alphabet on this edge and that edge, and we have a finite automata that only accepts the null word. As soon as we read a letter, we're out of the final state forever. Now here is a finite automata that just accepts one letter. Now it might be a little more complex than you think. You think, oh, it's just one letter, it should be pretty easy. With a transition graph, it would be pretty easy, but with a finite automata, we need edges exiting from every state. So when we read that one letter, then we go to the final state. If that's the only letter in the word, then we accept. But if there are more letters, then we get kicked out to this outer darkness state. And if the first letter is not the letter we're looking for, then we'll move to the outer darkness state and will stay there for the rest of the word. So now we have a finite automata that accepts the null word and a finite automata that only accepts one letter. Now what we're going to do is prove that we could take any two finite automatas and union them together. Now I have two finite automatas. I'll call this finite automata 1 and finite automata 2. What I want to do is I want to create another finite automata that accepts all the words that this one accepts and all the words that this one accepts. Now, if we look at this one, what this accepts is as we read B's, we stay here. When we read one A, we're here. If we read another B, we're back. But if we read two A's in a row, then we land in the final state, and it doesn't matter what comes after that. So this finite automata accepts all words with a double A in it. Now this finite automata, it depends on where we end up. The very last letter we read, if we've read an A, will be over here. And if we read a B at the very end, then we'll be over here. So this one accepts all words that end in B. So the union together means I want to accept all words that either have a double A in it or ends with a B. Now you could just kind of create a finite automata using your brain and create a finite automata that meets those two conditions. But what we need is a step-by-step algorithm that will create us a finite automata out using these two that will union the two together. So this is the algorithm we're going to use. Now you can read the steps of this on your own in the book. I'm just going to show you a demonstration of unioning these two finite automata together. So the step number 1 will be to create a new start state. And inside of it, I'm going to put x1 because that's the start state of this finite automata. And I'm also going to put y1 inside of it because that's the state for that finite automata. So what this means is I can be in this state or this state, either one. And what we're going to do is we're going to say if I'm in state x1 and I read an A, then I go to state x2. So I will draw this x2. I read an A. If I'm in state y1 and I read an A, then I'll go to state y1. So I'll put y1 inside of here, okay? And now I'll do the B edge for this state. If I'm in state x1 and I read a B, I stay in x1. And if I'm in state y1 and I read a B, I'll go to state y2. Now we'll keep going. We'll do it for this state, and we'll keep going until every state we create has an A and B exit. Now the one thing that we have to make sure is that we don't repeat these states. So let's keep going. If I'm in state x2 and I read an A, I go to state x3. And if I'm in state y1 and I read an A, I stay in state y1. And just making sure there's no state x3, y1 in any of these. So that's going to be a new state that we're going to have to figure out. Let's go ahead and try our B. If I'm in state x2 and I read a B, then I go back to state x1. And if I'm in state y1 and I read a B, then I go to state y2. Now if you notice, that's this state right there, x1, y2. So we don't want two of these. So we'll go ahead and draw an arrow to there and put the B edge and then erase this one. Now, if you don't do that, then you we'll end up going on and on forever. And that's obviously will be no fun. So make sure that you check that you're not creating duplicate states. Okay, let's go ahead and figure out the A and B exit for this one. If I'm in state x1 and I get an A, then I go to state x2. If I'm in state y2 and I get an A, then I go to state y1. Okay, so do we have an x2, y1? Yes, that's this state right here. So let's just draw that edge in. Now, if I'm in this state and I get a B, if I'm in x1 and I get a B, I stay in x1. If I'm in y2 and get a B, I stay in y2. So that is going to just come back to itself. And if you notice, both of these states, x1 and y2, both of them, when they get a B, they just come back to themselves. So that makes sense. Now we need to work on this state. If we're in state x3 and we get an A, we stay in state x3. If we're in state y1 and we get a B, we go to y2. Actually, get an A, we go to y1. Sorry, if we're in state y1 and we get an A, we go to state y1. So that is x3, y1. And if you notice, x3 goes back to itself on an A, y1 goes back to itself on an A, so that makes sense. Now, if I'm in state x3 and I get a B, I stay in x3. And if I'm in state y1 and I get a B, then I go to state y2. And do I have an x3, y2? I don't, so that's going to be a new state. All right, let's keep going. Now you might be worried, oh no, we might go on and on forever, but this is guaranteed to end sometime because all we're doing is different combinations of this state. So we got x1 with y1, x1 with y2, x2 with y1, x2 with y2, and x3 with y1, and x3 with y2. So we're guaranteed to just have those states at the end. So I promise this won't go on forever. But let's go ahead and do this state now. When we're in x3 and we get an A, we stay there. And if we're in y2 and we get an A, we go back to y1. And that's this state back here, so we don't need to add a new state. And now when we're in x3 and we get a B, we go back to x3. And when we're in y2 and we get a B, we go back to y2. So again, both of these stay where they're at. So we can just finish it like that. Okay, now that we are done and every state that we created has an A and B exit, this state A, B, this state A and B. So they all have A and B exits. We're almost done. We just need to find the final states. So, and anytime we land in x3, if we would have run this machine and ended up in x3, that would have been a final state. So we search through this entire machine looking for states that have x3 in them, and we mark them as a final state. Okay, same for this machine here. If we run this machine and we end up in a y2, then that would be in a final state. So any state that has a y2. Now, we already marked this state a final state, so it gets to stay. But here's another state with y2 in it. So we'll mark that as a final state. So really what we're doing is we're running these two machines at the same time. And really, we're pretending like, okay, I can either be in this state or this state. When I read a B, I go here or here. So that causes me to move to this state that pretends like it can be in this state or that state. And we just keep going until we got all of those edges, mark our final states. And now we have a machine that accepts any word from this finite automata or this finite automata. So that's just a live demonstration. Now you can read the book that says the step-by-step procedure to do this. And then because we can do this procedure on any two finite automata, not just these two, but any two finite automata that are created, now we know that we can always create a finite automata that unions two finite automatas together. So we've proven this part right here. So now our next lecture will prove this part and this part. And then once we've proven all of that, we've finished proving Kleene's theorem.